Welcome back. In this video, we will be seeing chaos in nonlinear systems with an example of the Lorenz system. In the previous video, we have seen chaos in discrete equations with an example of the logistic map and how to use discrete equations in an application. Please check the link of this video in the description box given below. Before we go on to understand chaos in nonlinear systems, first we'll find out discrete system versus continuous system. A discrete system is one in which the state variables change only at a discrete point of time. For example, customers arrive at particular points of time to the bank, say at 6:15, then 6:23, then 7:1, etc. That is, the value of the variables is independent of each other. In contrast, a continuous system is one in which the variables change continuously with time. For example, the amount of water flow in a river. Let us see the properties of the chaotic system. The first is sensitivity to initial conditions. That is, a very small change in the input produces exponential change in the output. Chaotic systems are deterministic. That is, it can be approached more systematically and can be modeled by mathematical equations and represented quantitatively. Hence, it is a deterministic chaos. Chaotic systems are continuous systems whose behavior is dependent on time. Here we consider the Lorenz system. It is expressed with the ordinary differential equation. This is the equation that represents the Lorenz system. Before we understand the Lorenz system, we first need to comprehend the ordinary differential equation. Let us have a quick recap of the ODE. It describes a dynamically changing phenomena. It is defined as a rate of change of quantities. So here the Lorenz system is represented with the ODE. It is a three-dimensional system whose dynamics changes with respect to time. So dx by dt is a rate of change of the point x with respect to t. Similarly, it goes for dy by dt and dz by dt. Another important parameters to be noted in the Lorenz systems are sigma, rho and beta. These are the control parameters. These values are very critical and influential because they define the behavior of the system. So as the values of the control parameters are varied, the dynamics of the system changes. For the Lorenz system, the control parameter values for which it is chaotic are sigma equal to 10, rho equal to 28 and beta equal to 2.667. The next remarkable property is the chaotic attractor. The trajectories of a chaotic system converge towards an attractor. These attractors are bounded and non-periodic and have a peculiar and intricate structure with a fractal property. And these attractors are chaotic in nature and has a butterfly pattern. Now let's see how to apply these sets of equations in an application. We'll compare with the discrete map for better understanding. Here, f of x is the discrete map. It takes xn as input and maps to the value xn plus 1. That's why it is known as a map. The output of the nth iteration is given as feedback to the next iteration. By performing such an iteration, we get the values of the chaotic map. Next is the continuous system, which is defined by dx by dt. That is, it gives the rate of displacement of a point x with respect to time. So this gives the velocity of the trajectory of the system. Here we can see the first equation of the Lorenz system, dx by dt is equal to s into y of I minus x of I, where s is the control parameter. Here I am going to use the Euler's method for getting the values of x. For this, we consider two parts. The first is the displacement of x in the previous iteration, that is x of I. The second part is the displacement produced in the current iteration at time t. So the second part is obtained by multiplying t to dx by dt, which is s of y of I minus x of I. So this is a pseudocode for applying the Euler's method to the Lorenz system. Here we consider dt is equal to 0.01. By performing these iterations, we obtain the values of x, y and z. And plotting them, we get the butterfly pattern of the Lorenz attractor. Thank you for watching and stay tuned for more videos on chaos.